So welcome everyone. This is one of the OERC seminar series. So my name is Michael Jack. I'm one of the co-conveners of OERC. And I guess if you want to be on our mailing list, we have seminars every month related to energy topics. If you'd like to be on our mailing list, please, if you're not already, so go. But we're very lucky today to have Anna Garden here from the chemistry department to give us a talk about fuels and fertilizers and catalysts and everything like that. So yeah, welcome and thanks a lot for coming along.
Great, thanks Michael. Yeah, it's nice to be here. So to give you a backstory, the reason that I am here is that I somehow found myself in the OERC mailing list. It was, but through all this mailing list, it popped up that there was a seed research fund that I wanted to apply for. I thought these were these little wee pockets of money. I thought it would be great to have these little wee pockets of money because I had a wonderful student sitting down the back there that I wanted to employ for a summer studentship to do a little bit of exploratory work to see if we could go further with the project. So we got this money. We did that exploratory work that worked out really well, and now we're continuing on with this project. So that's my success story, I guess, from the one day that I signed my name on the OERC mailing list. So I encourage you all to do the same. So what I'm here to do is to tell you broadly what my research group does, and I'll tell you a little bit about that particular project that I used the seed research money for to pay Ray, who's back there, to do some work for us. So I'm a chemist by trade, and I run a small little research group in the chemistry department. I've only been here for 2 years. Now, so we're still really just finding our feet and getting underway. But broadly speaking, what our research is in the field of heterogeneous catalysis, and specifically a computational approach to it. So some might say that I'm not a proper chemist. I will refute that and say that we are, but we just use somewhat non-traditional techniques to answer our chemistry questions. Okay, so some of these words may be a little unfamiliar to you. So what I'd like to do first is see if the clickable work will be the first. Should be turned on that side. No, probably not. No, it probably wouldn't kill me just to push the button here. Right. We'll just reboot it up, shall we? Can we stop the share briefly? Is that okay? Sorry, team. What do they say about a mechanic's car's always broken? Computational chemist computer never works. Which one? That one.
So do you want to do that from the get onto your first slide? Make sure it's working. And then I'll just that one. Yeah. Sorry, can we just this one?
Sure. Yeah. Right. Okay, I think we're under control now. Sorry about that, team. All right, so this is the outline of the talk that I would like to give you today. I would like to start by introducing this field of heterogeneous catalysis, so that you know what it's all about, what it's used for, what's difficult about it, and how we think that a computational approach really can help to solve some of the problems that we have. Then I really do hope that I have time to speak to you about 3 research projects that we've done, and I apologise in advance if we don't get through them all due to time. But I've picked these 3 sort of as an example of 3 different types of things that we try to do in our research group, and we're using these certain reactions to show them. So in the first one, we really do try to design new catalysts, and I'm going to show you how we do that with some work on the electrochemical ammonia synthesis here. Another thing that we're interested in doing is understanding the importance of various little sites on our catalysts that we have. And to do that, I'm going to show you an example about hydrogen evolution on taking nanoparticles. And then show you an example of, this is the work that I got the funding from you guys here for, to show you a really complex reaction mechanism and how we can use calculations to unravel that and then use that to go back to the start and design new catalysts. So, what is this thing called heterogeneous catalysis? Well, basically it's a form of catalysis where the catalyst and the reactants are in different phases. Now, the most typical form of that is that we have a solid catalyst, which is quite commonly a metal surface, such as shown here. And then our reactants, or the things that we're trying to catalyse, are liquid or gas things that flow over the top of our catalyst. So this is what's shown here. This is just an example of ammonia synthesis where we have nitrogen and hydrogen that flows over this metal catalyst surface to form ammonia. And it's really this little wee thing in here that forms the heart of some of these big industrial processes that are used at an enormous scale around the world. So, excuse me, this is an ammonia plant in Ludwigshafen in Germany. And there's a lot of bells and whistles here, but really this is the bit that's doing all of the interesting things for us here. So these catalytic processes are important in a lot of existing processes, particularly for industry. So as I said, for ammonia and sulfuric acid, which is sort of two of the most largely produced chemicals worldwide. But it's also around on a smaller scale. Probably most people's vehicles will have some form of catalytic system in them by way of a catalytic converter, which is this mechanism that is in the exhaust system. So the exhaust fumes flow over the catalytic converter, take some harmful gases and turn them into slightly less harmful products before they're spat out the back of the car. So these are examples of where these heterogeneous catalytic processes are already in play. But what we like to say, especially when we're trying to write grant proposals, is that we try to say that there's a whole lot of other reactions out there that could possibly be made to work if we can just find the right catalyst. And sometimes we call these dream reactions because really if we were able to do them, then we'd be able to move to a more sustainable type of future. So producing, say, low cost and low carbon fuels. Asymmetric synthesis is more of a chemist application of these things. But we like to think that this really is, this heterogeneous catalysis is the key to a sustainable future. Okay, so it's great, right? Hopefully I've convinced you of that. But that doesn't mean that it's free from challenges. As with any important process, usually there's a fair bit of mountains that we have to climb along the way. So one of the challenges of heterogeneous catalysis is that the reaction that we're trying to catalyse is often a complex multi-step mechanism. So just as an example, this is showing you the electrochemical reduction of carbon dioxide to methane on copper. When we write down a chemical equation that looks like this, it looks reasonably innocuous. We have CO2 that just basically goes pop and turns into methane, magic, just like that. However, in reality, what has to happen is the CO2 has to adsorb onto the surface of the catalyst, and then it has to hop along, bump, 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 along this pathway with various intermediates until we finally get to the product there. So there's a bit more to it than just turning one thing into another in a single step. And actually, this is the good version of the story, because actually this is more like what the reaction network for reduction of CO2 on copper looks like. All of these are different possible intermediates at every single step, and the optimum pathway is that that's shown here in blue. So if we want to understand this reaction of turning carbon dioxide into methane on copper, we don't just have to understand the energetics of this bit here, but we have to understand the energetics of all these possible competing steps as well. So this is a real challenge when we want to understand and then optimize or design a catalytic system. So the second challenge that I want to mention is really more of a pragmatic challenge. If we're trying to design a new catalyst, we're trying to come up with a material that might be able to do what we want it to do. As chemists, this is our toolbox basically that we have to choose from, and pragmatically there's just a lot of possible catalysts. So mostly we pick catalysts from the D block of metals here. Even in there's quite a few. Then we can have alloys, we can have oxides, nitrides, sulfides, different crystal facets, different forms of the catalyst, you name it. We've got a seemingly infinite array of products to choose from. So why theory then? Is theory something that can help us surmount some of these challenges? Now, there's a personal reason why I do theory, and that's because I stepped into a lab once and only once during the course of my PhD, and that was the result. Okay, so this is the reason that I myself do theory, because I do not like to be in the lab and nothing good happens when I go into a lab. So I like to say that computational chemistry is really great for a clumsy chemist, but there is actually more reasons than that why we might like to take a computational approach to this problem. And basically what we can do with a computational approach is we can understand what we call the microscopic reaction mechanism. So of all these complex intermediate reaction steps that we have here, we can map out the energetics of those steps one by one by one. And it's actually quite often very difficult to get this kind of information experimentally to be able to look and break down every tiny little part of the chemical reaction. So we can do this. And then pragmatically, again, we can just more quickly often screen through that big pool of possible catalysts a lot faster than the students could do in a lab. So that allows us to basically cut down the pool of possible catalyst materials that we could have and then refine it to a few possible ones which we could then go over and test in the lab. So this is what we do. We perform all of these simulations, and we typically do it on these big clusters. So we don't do much of it on our desktops or our laptops, except if you're the guy over there in the corner that had, I don't know how many computers running simultaneously when we couldn't get access to this. But anyway, most of the time we work on these big clusters, we send away our calculations, come back and analyze the results. Okay, so that brings me, that's sort of an introduction to what we do and why we do it. So I'd like to now talk about the first problem that we've been trying to work on, and this was what I largely did during my postdoctoral fellowship at the University of Iceland. What we were trying to do, our goal here, was to see if we could find a new catalyst for what we call electrochemical ammonia synthesis. So before we launch straight on into that, let's give a little bit of background about this problem of ammonia synthesis. So as I mentioned in the introduction, ammonia is one of the chemicals in the world that's produced on the largest quantities. And this has been the case since about 1913 with the introduction of the Haber-Bosch process. So we've got Fritz Haber and Karl Bosch here that received the Nobel Prize for this. Basically what this industrial process allowed to occur was allow for the production of ammonia at really enormous quantities. So when that was brought in, all of a sudden we could make a whole lot more ammonia. We could use that whole lot more ammonia to make fertilizer, and that's the real key, and that's a big worldwide use for ammonia here. So then if we could make a whole lot more ammonia-based fertilizer, then shown in green here, well, we can consume a whole lot more of nitrogen-based fertilizer. And if you want to look at least the correlation with the world population, then we can also feed a whole lot more people. So this process has been really important to feeding more and more people on this planet. So the way that this process works, so how do we actually make ammonia? Well, basically we take nitrogen and hydrogen molecules, so N2 and H2, pass them over the surface of this catalyst, break them up and recombine them to form ammonia molecules here. This is really difficult to do, this reaction here. N2 is not an easy bond to break, so we do need the catalyst for this. And what's more, we do need to kick the temperature up quite a lot. Okay? Doing this at ambient temperature doesn't get the reaction going anywhere nearly fast enough, so the temperature has to be raised relatively high. Unfortunately, with the temperature going up and up and up, what happens then is we don't get as much product formed for this particular reaction. So what we have to do is we have to lift the pressure up to combat that. So we have the temperature up to get it go fast enough, the pressure up to get enough of the ammonia. And these are about the conditions that we get, I think, about 10% conversion of nitrogen to ammonia. Anyway, high temperatures and high pressures, and particularly high pressures, are really not a great way to be making things if we're worried about sustainability, if we're worried about energy use, and just basically difficulties with infrastructure. So if we're going to rate these on a smiley face scale, I would give this a pretty big frowny face, really not being the best way that we would like to be doing these kind of processes. So there's another problem as well, is that as one of the reactants, we use this hydrogen gas as a reactant. And the way that we get hydrogen gas usually, and it's not the only way, but usually this comes from natural gas, which is a finite resource, which we'd really rather not use if we could help it. So 2 smiley faces, sorry, Haber-Bosch process, we're going to cut you at this point here. So this got us wondering, well, is there a better way? Is there a way that we could make ammonia that's not this Haber-Bosch process? And as it turns out, in nature, there's already something there that does it. As usual, nature does things a little bit better than we do, and we just desperately try to chase along and catch up and copy where we can. So the enzyme nitrogenase catalyzes again the conversion of N2 nitrogen into ammonia. It looks like this is this big messy looking protein, and the bits that really does the interesting catalysis is what's called the FeMO cofactor, or FeMO-co sometimes. Looks a bit like this, sticks the N2 on, turns it into ammonia. Now this is the chemical equation for the conversion of N2 to ammonia, and there's a bit of a key difference here. Rather than having H2 as a reactant, what we have here is we have protons and electrons here. When we have a reaction that has protons and electrons like this is an electrochemical reaction. So it's a slightly different way of doing it here. And the best thing about this is that this enzyme here is able to facilitate this conversion at a temperature of 20 degrees and ambient pressure. So this gets a very happy looking face here, because these are these ambient conditions. So this really spurred us on to this idea then, can we perhaps build a man-made setup, if you like, a man-made electrochemical setup that could possibly catalyze this reaction using electricity, protons, and N2. And that's what we set about trying to do during my postdoc. So there are this isn't the only enzyme in nature that catalyzes an electrochemical reaction. There's a whole host of them. I barely know what they are because I'm definitely not a biologist and these things are a bit frightening. But regardless, there's an enzyme called Heterogeneous that converts protons and electrons to H2. Photosystem 2 is able to split water into oxygen, protons and electrons. And one called CO2 reductase takes carbon dioxide and reduces it into methanol. And for all of these processes here, we've been able, not we obviously, but man has been able to find some man-made catalysts that can mimic the process. So for combining protons and electrons into hydrogen, a platinum catalyst will do the job. To split water into oxygen, protons and electrons, ruthenium oxide is a good catalyst. And to convert CO2 into methane, so it's not methanol, but it's close, into methane, copper can do the job. So what we really wanted to try to do was find that magical mythical catalyst that might be able to do this reaction here. So as I said, calculations are quite a good way of doing this, and my postdoc advisor was looking into this back in 2012. And basically the point of view that we wanted to come at this problem, the way that he started it then and then we continued it, is we really wanted to make the simplest possible catalyst material that we could. A lot of people are looking into this problem, but there's a lot of incredibly complex types of catalysts and electrolyte and electrode systems set up to do it. But we wanted to look for the simplest possible thing we could to have the greatest possibility of getting widespread and cheap usage here. So what we used both in my advisor's study and in our subsequent studies was a method called density functional theory, which for your purposes here, we can just think of as a computer simulation method, to previously screen through a bunch of pure transition metal surfaces for being possible catalysts. Now the pure transition metal surface is basically the simplest possible catalyst that you could come up with. So that's what they did. So they screened through all of these different surfaces, just as shown up here and there with their chemical symbol next to them here. The horizontal axis is not particularly important, it's just spacing those different materials out so that you can see them. It's this axis here that's really important. So if you're higher up on this axis, so this is the potential or the voltage that you have to apply to get the ammonia to form. So the higher up this axis is, that means the lower voltage that you would have to apply to be able to form ammonia on these catalyst surfaces. So what you can see is that the likes of rhodium and ruthenium are pretty high up here on this, what this is so-called a volcano pot here. So for these, we wouldn't actually really need an awful lot of potential or voltage to get this reaction to go to make ammonia. However, superimposed on this figure here, we've got this grey area here with an H and a white area here with an N. What that means is that for everything that's under this grey region here, what will actually preferentially happen rather than forming ammonia is that that whole of that surface is going to get covered up in hydrogen. So we're saying that if we didn't have this problem, then we'd be able to form these nice and easily and quickly, but as it happens, the whole surface gets covered up in these protons. So and actually the ones that are left over here, turns out a lot of these form oxides. Okay, so the ones that don't cover in hydrogen form oxides. So it's really not looking that great. So what that really says is that you might form some hydrogen, but you're certainly not going to form much ammonia in here because you just simply can't get the nitrogen onto the surface because there are too many protons in the way. So that led us to where I came into the piece, and we went, well, if it's such a problem then to try to get onto the surface, why don't we actually take a material that already has nitrogen in it? So then what we could do is we could react one of the surface nitrogens here, turn that into ammonia and put it back later, thus completing the catalytic cycle. So that's what we did. We chose this class of materials called transition metal mononitrides. So this is just that goes metal, nitrogen all the way along the surface here. And we investigated the formation of ammonia by what's called the Mars-Van-Ketteler mechanism, or a Mars-Van-Ketteler mechanism. So just to step you through this here, so now we're looking down, sort of down on top of the catalyst here. What we have is we have 1, 2, 3 protonation steps where we can pop a proton on a nitrogen here, another one on there, and another one on there. And these are our optimized configurations from our simulations. So you can see when you start to put 2 or 3 hydrogens on that nitrogen starts to get out of that surface and move away here. So what it does at this step then is it completely desorbs from the surface, and now we've got a hole left. So one of these nitrogens is gone. So we have a vacancy on the surface. So what we can do at this point then is N2 can come along and replenish that vacancy. So one of the nitrogen atoms will pop into the hole, and the other one will just sit next to it on the surface of the nitride here. So that's this one here is now sitting on top of the surface here. What we can do then is just go bam, 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 3 more protonation steps on this one here, desorb that nitrogen, and we're back to where we started. So this was a mechanism of ammonia formation that we were investigating to see if any of the possible transition metal nitrides could form ammonia in this way. So we used our computer simulation method, DFT, again, and we investigated 100 different transition metal mononitride. So we basically took anything that was in the D block here, and we took 2 different crystal structures, the rock salt and the zinc blend, and 2 different facets of each of these, 100 and the 111. I think there might be a 110 facet of the zinc blend here. So we introduced a few criteria then for a catalyst to be what we would call a suitable catalyst for this process here. The very first one is a blatantly obvious one. To be a good catalyst, it must actually be able to make ammonia with not very much electricity. So that's a bit of a no-brainer there. But we introduced another few criteria that are perhaps not immediately as obvious. Firstly, we said, well, if we're going to be connecting up some electricity to this and whizzing it through, well, we need for the catalyst to be stable when we apply voltage. Makes sense, it can't decompose. This one here is going to take a little bit more explanation, which I'll get to shortly, but we need for the surface of the catalyst also to be stable for the whole catalytic cycle. And I'll explain that in just a second. And we need to make sure that anything else that we have kicking around in our reaction mixture, because we're in a solution with water here, that our catalyst doesn't get poisoned by any of those. So I'll step you through these. I'll try not to go on about it for too long. But basically, in the first instance, what we did is we did what I was talking about earlier, that we actually calculated the energetics of every single one of those steps in the mechanism. So we see that it goes up, 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 up. Sometimes it goes up, sometimes it goes down. So we get a free energy diagram for the reaction that looks like this. Now, when we have these kind of reactions here, whenever we have a proton and electron transferred in one of the steps, like we do for a lot of these steps here, we can actually eliminate any of these uphill difficult steps if we apply a voltage of that same amount to our system. So what we look at here, and we see, well, the biggest uphill step here is 0.76 electron volts. So what we can do then is we can apply a voltage of negative 0.76 volts that shifts the whole thing up, and it eliminates those uphill steps where possible. There are, as you might be able to see if you look closely, there are a couple of little uphill steps that we can't eliminate, and those are ones that don't involve a proton-electron transfer. So there we can't, adding a potential won't affect that at all. So we just have to live with that for some of those. Anyway, we mapped out this free energy diagram for all of our catalysts, and we found, so this is zirconium nitride, we only have to add that negative 0.76 volt potential, which is actually quite good. That's not an enormous amount of potential to put on to get this reaction to go. So that looked great. So in the course of doing this part of the study, though, we found that some of them, so these ones that are shown in blue, these were actually unstable at the required potential. So, for example, we found out what potential we had to apply to get the reaction to go, and then we did a wee back of the envelope calculation saying this is going to be stable there. Some of them, no, it's not. So they get struck out at that point here. Some of them, these ones that are shown here in red, when we popped the protons on them, now we put no restriction on where they could go, and for some of them, they would just cover up all along the metal atoms, and we wouldn't get multiple of them sticking to the same nitrogen to form ammonia. So for some of them, the surface just kind of get packs on with hydrogen, so we're actually just going to form H2, not ammonia. As it turns out, one of these turns out to form H2 quite easily. So as a nice little side to that, we found a catalyst that might be a good hydrogen evolution catalyst. So I like the serendipitous aspect of science. Sometimes something doesn't work for one bit, but it works for another. Okay, so this was the one of the other criteria that I said might need a little bit more explaining. And that's that we require the surface of the catalyst to be stable. So when we think about it, if we form this, so now, sorry about all these different views, but now we're looking side on to the catalyst. So here's the surface layer in here. So what we have is that we protonate successively one of these nitrogens, and out comes the ammonia. And at this point, we had that hole or that vacancy left in the surface. Now, ideally, what we wanted is that that vacancy would be filled by N2 coming into our reaction mixture, into that hole there, but there's actually a competing process. And what can happen instead is that that hole or that vacancy can be filled by migration from a nitrogen in a layer slightly below it. And that can come up and fill in that hole there. So then that nitrogen can be reacted to form ammonia. So we have another vacancy, and now this can pop up from the surface below. And this can go on and on and on until eventually we have nitrogen left. Now this was spurred on, thankfully, by one of our experimental collaborators that did this and found this was a problem, so we built this into our study. But basically they tried this with a catalyst and got terribly excited because there was all this ammonia being formed. But when they did some isotopic labeling, so basically labeling these nitrogens as one thing and these nitrogens as another, they could then, sorry, not these ones, the ones coming in from the gas phase, they could see that all of the ammonia that they eventually formed had the signature of that nitrogen that was in the material. So now we just have kind of a convoluted reactant. We don't have a catalyst yet. And this was a problem when we put this into our screening calculations for all of these nitrides here, so they were cut out of our study as well. Finally, this is quite a straightforward one. We just simply looked at whether any H, OH or O floating around in the system would preferentially absorb in that vacancy. Turns out for a few of them it did. So those were cut because the catalyst would be poisoned and they wouldn't be any good. So the summary of that is that after we cut all of these out, and I don't know why they fade in a dramatic manner, but when we cut all of these out, it turns out that we only had 4 left that didn't cause any problems for us. And the good thing is that the 4 of those not only didn't cause any problems, but some of them actually could form ammonia with quite low potential. So that's what's summarised in this table here. You don't need to look in close detail about what everything here means. Basically, the point is that anything that's green is good, anything that's red is bad. But what we've done for each material is we've listed each of those facets that we possibly tried. And this is really important because even if we want this single crystal perfect surface of a catalyst, often we don't have that. We can have a polycrystalline sample, or furthermore, we could use a polycrystalline catalyst because it would be cheaper and easier. So what this tells us is that basically for zirconium nitride, it's green all the way along, so we're kind of okay with this one. When we've got these red ones, the problem is, so for vanadium nitride, for instance, it was our best one in the terms of that we only need to put about -0.5 volts in to get ammonia. You've got to be very careful that you don't have any of these facets present, otherwise the whole of the catalyst is going to decompose. So that one would be better, but it's a bit more of a faff because we have to make sure we don't have this. Zirconium nitride, it's a lower current efficiency, lower higher potential, but otherwise it's looking pretty good. So that's where we got to with that before I left and took up this job over here, but we haven't finished yet. So this is Ray, who you will learn to know because Ray has been involved in almost everything that I do, always, which is wonderful. It's great to have around. But what Ray started doing, was it last year, Ray? I think last year, started looking at what happens if we've got a defect in these catalyst surfaces, because often a defect can really change your reactivity. So what Ray was looking at was basically if you had this defect, which we modelled as a little step, how does that change how we form ammonia on these surfaces? So Ray started off doing that, and that's been carried on by some students over in Iceland. And another thing that they were up to over in Iceland was trying to get a bit more realistic about the electrochemical environment and the water, the solvent that we have in here. So at the same time, we have some experimental collaborators, these fine-looking people here, that have built up an electrochemical lab for this purpose. And because in Iceland they've got this thin film growing expertise, so what they're doing at the moment is growing up some of these promising catalysts, starting with vanadium nitride, and testing them to see if we actually can form any ammonia. And there's nothing that's up to publishable quality yet, but the initial results certainly seem very promising, and we are getting detection of ammonia. So it's been a really fun and exciting project to be a part of, and it is definitely one that you can see the end result quite early, which can be quite rewarding because you really can see that it could be used and could have practical use quite soon. So that's one of the ways that we work with catalysts in our group, but I'm a bit of a puzzle geek and actually kind of like just really trying to figure things out rather than necessarily making something with this immediate commercial or practical application. So this project here, I wanted to tell you a little bit about how we really wanted to get in a little bit more in detail to understand just what features on our catalyst were involved for reactivity and how we could manipulate these if we manipulated the shape of the catalyst ever so slightly. So I'd like to tell you now about hydrogen evolution on platinum nanoparticles. So nanoparticles, for those of you that don't know, are basically, well, nano being a prefix meaning very, very small, they're just very, very small particles. So for a platinum nanoparticle, it's basically just a piece of platinum that's cut down very, 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 very small on the nanometer scale. So nanoparticles are a good and interesting catalyst for a number of reasons. One of them is that simply when you cut down what would be a big bulk piece of metal and cut it down into lots of tiny little bits, you have an awful lot of surface area. So it's on the surface that all of the catalysis happens. So basically you have more of your material can do a job for you, okay? So there's just less wastage of material in that sense. But from our point of view, the really interesting thing about nanoparticles as catalysts is that they have a whole lot of edges and corners. And it's these edges and corners and steps and kinks and defects that often actually really dominate the reactivity of a given catalyst. So what we would really want to do if we want to have a very active catalyst would engineer some material that has a high density of these types of sites. And luckily nanoparticles can do that for us without us having to get into anything a bit too fancy than that. So hydrogen, the interaction of hydrogen with platinum nanoparticles has got practical relevance because platinum is an excellent hydrogen evolution catalyst. So if you're looking at fuel cells, a lot of reduction reactions, electrolysis involve a platinum catalyst and hydrogen in some way. So it's really good to understand how this might work. But it's also used as a model system to study reactivity because it's relatively simple. The formation of hydrogen is it's basically as simple as you can get in terms of chemical reactions. One hydrogen plus another hydrogen equals two hydrogens. We can probably cope with that. So we can actually learn a lot about various catalysts by studying this very simple reaction. So this is an example of a commercial catalyst. So this is a platinum nanoparticle catalyst supported on something called XC72 Vulcan carbon. This is just an inert carbon support. And these dark blobs here are the platinum nanoparticles here. So typically between like 3 and 10 nanometers, although it can vary quite widely. So what we want to do is we want to model this reaction, so two hydrogens on the surface of these particles coming off like that. So from a modelling point of view, this picture doesn't really help us that much because all we see here are reasonably indiscriminate black blobs. So we need to do a little bit more than that if we need to build up a model of our catalyst to use. So what we do is we turn to our friends, and this is from some colleagues of ours in Birmingham in the UK, that have got this really high resolution microscopy available to them. It's not just them, there are other groups around the world too, but what these here are 3 different microscopy images, and if you look at the scale bar here, now we're looking at 1 nanometer, so these are only 1 to 2 nanometers across. These things, they're tiny. What's really impressive about these as well is that they know that this has 309 plus or minus 6 atoms, so that's quite nice and precise. I like this here. I still find this quite neat. That thing circled as a single atom. I still find it kind of neat that we can see single atoms, but maybe one day I'll get sick of that, but not quite yet. So if you look at these, so these are just a collection of gold nanoparticles. You can see from them, especially if I put this eye-guiding helpful red lines around them, that you can sort of look at them and they look like kind of regular polyhedra, these things. If you look, shall I take the red ones off now so that would have trained your eyes? So this one looks a wee bit hexagonal, I would say. This one's got quite a square outline, and this one is much more, what did I say, that's pentagonal, that one's much more hexagonal. So that tells us a little bit more than the previous picture. Rather than just indiscriminate black blobs, maybe we need to start considering sort of regular polyhedra in terms of our suite of possible nanoparticles. So that's what essentially we do. And these are just a very small sample of the types of polyhedra that are possible. Up the top we have 3 different shapes that are all formed of the same number of atoms. So we have an icosahedron, a decahedron, and a cuboctahedron. And this is just to show you what types of outlines that they would show if you looked at them, under a microscope like that. And then what we do have down here, now we're looking at slightly different numbers of atoms, and these are all different types of octahedra, basically, where we've cut off the corners to differing degrees. So if you look at these and the myriad other possibilities that we have, if you look at them with a catalytic eye on you, you can see that there's lots of different types of faces, there's different types of edges. Here's one, that one looks a bit different. There's lots of different types of corners. Here's a spiky one, here's a much more stubby sort of one. So what this tells us is that in this suite of particles, there's really a whole lot of different types of active sites where our reaction could take place. And that means that there's possibly a whole lot of different types of reactivity that we might expect if we have these different shaped particles. So this is just a little bit of a close-up, just to get some definitions for you. When we're looking at these potential active sites, so this is just a zoom in on one of them. So this is what we call an FCC particle, so one of our octahedra. You can see we've got this grey face here and this darker grey face here, so we've got two types of facets present. We've got a couple of different edges. So we've got this A edge, the red one here, which is where a 111 facet joins a 100 facet here. And we've got what we call the B edge, so where we've got 2 111 facets joining like that. On top of that, we've also got the corners. So if we want to understand the activity of this particular particle, we've got to understand the activity of all these various bits and pieces on the surface. So, good, we know what they look like. We've got an idea that we're interested in these active sites. However, we've still kind of got a problem, because 3 to 100 nanometers of these types of particles, we're looking at over 1,000 atoms. What's more, we're looking at over 1,000 platinum atoms, which, you know, your periodic table means that you're going to be dealing with a whole lot of electrons, which makes life a little bit difficult from a modeling point of view. So this is really prohibitively expensive to study with our traditional methods. So what we do instead is we use these much simpler model systems where we can basically build little models of the various edges or faces or corners that we want. So here's an example. So we use model systems with a periodic array of the active sites. So here's an example here where we have a platinum surface here. And what we've done, we've taken a 110 surface here and peeled away every second row of atoms along the top of that surface. So by peeling away a row here, and a row here, and a row here, we expose these little mini edges here. So we expose a little 111 face and a little 111 face here. So what we have here is a model for a B edge here. So this surface here has a rather mouthful of a name. It's called the missing row reconstructed platinum 110 1x2 surface. It's a mess. What I'm going to call it instead is I'm going to call it the B11 edge because it's a B-type edge, because it's two 111 facets meeting, and it's only got one atom before it turns around and starts to make the next one here, so it's not very big. So this surface here has been studied both experimentally and theoretically because it's a common surface, but also because it is often cited as a model for nanoparticle edges. And there is really good agreement with the theory and the experiment that's around for the surface in terms of how hydrogen interacts with it. So here's a couple of studies if you're interested. So what we wanted to ask though is that B11 is really the smallest possible model for a B edge that you could get. It just has one atom before it turns around and starts zigzagging away again. So we wanted to ask the question, how well does that actually represent true nanoparticles? So what we looked at was the B22, the edge 3344, blah, blah, blah. We just extended this edge up to see if we could see convergence of the properties to what might be a more realistic model of the edge. But probably more interesting question for us to ask was, well, what about those other types of edges where we have a 111 facet here actually meeting a 100 facet here? How does the activity of this edge differ from the activity of this type of edges? Because both of those are present on our particles. And that's what we were looking at in the study that we published back in 2014. So we used some mouthful of acronym types of methods here to calculate actually the reaction paths for hydrogen starting on the surface and going up, 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 and eventually coming away as H2. We did this for a range of different coverages, so with no hydrogen on the surface, with others around, we basically considered a lot of different possibilities. So in regards to the first question about, hey, is this B11 a big enough model for actual real-life nanoparticles? What we found is that when we're at intermediate hydrogen coverage, we actually found that rather than coming, so I'll try to use my hand as an awkward model, rather than the hydrogens coming off the edge, they were coming off from the middle of the facet. But when we increased that model size, even up to 2,2, 3,4, 3,3 and 4,4, then we started getting them all desorbing from the same site on the nanoparticle, and by B3, 3 and 4 we were converged with respect to those energies as well. So what that told us was that this is actually far too small a model to be useful for actual nanoparticle edges, and you really should kick it up a bit. At least even just one more row of atoms will get you a lot more realistic here. So that's a bit of a pedant sort of dot I and cross T kind of thing, but the more interesting thing was when we came and had a look at how that B edge and that A edge differed in their reactivity. And this is what is shown here. So the two grey dashed lines are just the activity for the facets here, and the red one shows the energy as you pulling the hydrogen up and away from the surface, and the blue from the A edge, and the blue one is you pull the hydrogen up and away from that B edge. So what you can see here, the really important quantity here is the distance from 0 up to there for the B edge, and 0 up to there. So the highest point on the path is basically what you've got to put in to get this to go. And what you can see is you've got to put in significantly less energy to get that B edge to go. And actually when you transfer this to a rate, not just energy differences in these barriers, we find that this is enough to confer a 10 to the 5-fold difference in activity between these two edges here. So what this is really telling us is that not all edges are made equal. So we shouldn't really just go, here's a model for a nanoparticle edge and infer all of our information from that, but rather we do need to consider the different types of active sites that we've got to get the right answer. But probably more interestingly, what this is indicating to us, at least to me, is that we might be able to harness this difference in activity to really tune to get the most active catalyst that we can. So in this case where our blue one was much more active than the red one, what we could assume then is that this particle that actually has blue edges should be much more active than this one here. So with the types of controls that experimentalists are getting these days, I mean, you saw this ±6 atom that our experimental colleagues could select, if we can inform where we're likely to see these ones, where we're likely to see these ones, we can then inform experimentalists to synthesize the most active particles that we would predict. So that's sort of where we're at the moment, is that whenever we do any kind of catalysis now, when we're considering nanoparticles, we do consider a suite of possible active sites. And sometimes we consider the suite of active sites in terms of what type of edges and things do we have present. But we've also started to incorporate some explicit structural optimization of some of these nanoparticles to get an even more detailed idea of what's going on. But we'll get to that in a couple of minutes. So that was something that really told us what we should be doing should we want to consider nanoparticles as catalysts. So the last thing I want to spend hopefully only 5 or so minutes telling you about is this last project, which is an example of how we can have a really complex reaction mechanism that throws us a number of different challenges and how we can actually overcome those calculations to learn more about the system, which we then intend to use in the future to design new catalysts. So I'll tell you about what we've been doing on the reduction, electro reduction of carbon dioxide. Okay, so I don't need to tell anyone, absolutely, especially in this room, that we have a couple of challenges related to energy these days. We're largely in a fossil fuel economy. These fossil fuels are going to run out relatively quickly. Plus, burning them produces carbon dioxide, which is not great for our atmosphere and for our climate. So one proposal has been to sort of circumvent that would be, could we possibly take the carbon dioxide that we're emitting here, and can we convert it into hydrocarbons or alcohols so that we can then use that as a fuel from which we could capture the CO2 again and feed it a background in the so-called carbon neutral cycle. So this is the basis of the proposed methanol economy. The other thing is that we could possibly take carbon dioxide and make not just methanol, but we could make a whole lot of sort of synthetic hydrocarbons that could be used in high-value chemical industry. So from this point of view, this is hard. Capturing CO2 is not a simple task, but that's not what I'm interested in. It's getting better, I understand. But one of the other hard bits of the problem is this bit here. How can we actually get that reduction of CO2 into something that we can use either as a fuel or as a chemical building block? So one of the possible ways of doing this is with electro reduction. So just like I was telling you about with the ammonia synthesis example, an electrochemical reaction where we can have protons and electrons to convert CO2 into, well, probably best case scenario, methanol and water. So we hope that we could, by doing this, we might be able to find the right catalyst that could take CO2 and convert it into HCA, so actually to find out a hydrocarbon or alcohol of our choice with a relatively modest amount of energy. So that's what we were trying to do. And this has been going on for really quite a long time here. So now this is, what I've got here is an example of an experimental study back from 1994. This is one of the seminal studies that was done in trying to look at the catalytic activity of pure metals for CO2 reduction done by Hori. So I'm sorry that it's in a table, but in 1994 there was many more tables and colourful pictures around. But what you can see is here is a whole lot of pure metal electrodes. And basically what they did was ran this experiment until they're at a constant current density, or basically a constant rate, and looked at the potential required to do that, and then looked at the percentage of products that were formed in this experiment here. So there's a lot of numbers that you can see here, and there's a couple that are really key to look at here. First of all, if you look down the CO column, all of this group of metals largely makes carbon dioxide and not much else, a bit of formate, but not a lot else. If you come into this group here, we're largely forming formate here, and in this group here, we're largely forming hydrogen. There's a whole lot of zeros basically in any of these carbon-containing compounds here. However, if you look at the copper here, copper is really, really unique amongst these pure metals because it forms significant amounts of ethylene and methane here. Still some hydrogen, but very little of anything else. So it was a question for a really, really long time about how is it that copper, what is it about copper that's really unique that imparts this activity that it can actually form these carbon-containing compounds as opposed to primarily hydrogen or anything else. So this was 1994. Of course, there are better and better experiments as we go on with time, and this is just an example from 2014. So here we were just looking at a constant current density, and now here is scanning over a bunch of potentials and mapping up how much methane each of the metal electrons form and how much methanol each of them form. So again, the only one that really stands out of all of these is copper, the blue one. When you get to potentials of about -1 volt, then we start getting significant amounts of methane formed. So this really corroborated these experimental findings here. And it does beg the question of what is it about copper, what's happening here that allows it to form methane. So whenever we have to ask this question of why in terms of catalysis, the very first point in understanding why something works the way that it does is we really need to figure out the mechanism by which carbon dioxide steps through all of its little bouncy steps that I showed you earlier and turns into the observed product, which in this case is largely methane. So there's been a lot of work that's been done in trying to elucidate this mechanism, trying to figure out what does carbon dioxide turn into, then what, and what are the energetics involved in getting it out the other end. And granted, I'm a little bit biased because these are my friends, so I will say that only very recently this has been decisively shown, but my colleagues here have actually recently done one of the first studies that it's actually been able to get really good agreement on the rate and the product distribution. Anyway, what I'll show you here, so in this top trace, so this is one of these free energy diagrams where we go bump, 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 bump to the various products. And this bit at the top here, this is when we perform the simulation with no water around, so we just have the metal surface, the copper surface, and the adsorbates on top here. And the energetics are given by these coloured bars all the way along there to methane. And there's no little hoopy bars along the way, so we're not considering those high points along the path, just the beginning and the end of these paths here. So what you can see, if we don't include water, and we don't include those barriers, what happens is we predict to go from CO2 through this CHO intermediate down to CH2O and all the way along there. We predict going by this red path here. This model actually gets the onset potential for reduction pretty good, but the problem is that it's been experimentally shown that this guy here is actually not an intermediate in the reaction. So it predicts it gets some parts of it right, but we think it accidentally gets some parts of it right because it goes by a way that experiments say, no, it doesn't go through that way at all. So what my colleagues here at the University of Iceland did is that they included explicitly a water layer in the simulations and looked at the individual barriers to go through each of these steps. So this is a little bit what it looks like here. It's a bit small and a bit awkward, but basically we've got this mess of a water layer above the system here, and what the purple indicates is actually just the protons being transferred from the water layer onto the carbon-containing adsorbate here, and it hops along here like this. So when you do this, now our barrier here, this is the bit that we do to choose our path, is we find the lowest point, the lowest hump on these branching paths. You can see the green one here is favoured, so it's going to go through the CHO, and we don't get this flow formed at all, and way it goes down to produce methane there here. So that's the mechanism that they predict, at least at this potential here. And then this can be converted, so this can be done at a lot of different potentials, and then we can convert all of these various barriers into actually the current density or the electrochemical rate. And this is what they see here. So the lines are the production of hydrogen as a function of potential, and the blue ones are methane. And yeah, so the lines are theory and the dots are experiment. So you can see for the blue dots and the blue lines, for the theory and experiment for methane, it's really remarkable agreement with the measured rate with what's predicted from this model here. Hydrogen's off a little bit, and it looks awful on the scale here, but that's because there's an exponent involved in there, which always makes things a bit worse. But this is actually, on balance, really good agreement for this one here. And what they're able to see here is actually the reason why we have more methane produced than for hydrogen, because for copper, this hydrogen line stays here. So at this point here, when we go down in potential, all of a sudden now we have a whole lot of methane being produced here at this point. So that's the explanation of why copper produces methane at this potential here. It's basically the competition between these two lines here that's really well captured by this theoretical model. Now, I'm running over time a little bit, and I've just told you what everybody else did to do with this, but this is where you guys came in and given me a little bit of money, is we wanted to ask a couple of questions to do with this, because I've sort of brazenly said we use some computational approximation or computational methodology. Turns out what we do, whenever you do some kind of computational modelling of atomic or electronic systems, we can't solve them exactly. So if you've done physics, you'll know that the Schrödinger equation for many electrons is insoluble. So what we have to do is we have to introduce approximations. And within this larger approximation called density functional theory, we sort of say it comes in these different flavours or these different types of approximations. So what we wanted to ask the two questions here was, did we simply just get lucky, or we, my colleagues, get lucky in their choice of approximation that happened to give it this remarkable agreement with experiment? Was that accidental, or is that robust enough that we could fiddle around with that approximation a little bit and still be able to reproduce the results. So that was one really big important question. And then a bigger question, I guess, is how big are the error bars on this? So when we actually do make diagrams that look like that, they're always going to have a little bit of spread. How big are they? What can we say for sure? And then could we go on to design new catalysts with any kind of certainty or not? So that was what we were tasked with. And we chose to compare the current approximation, doesn't matter what this means, with a different one that we believe to be better because it's including van der Waals interactions, but it also allows us to make an estimation of errors. So this is what Ray was doing. Ray down the back again. And the bit that you guys paid me to do was basically be a wee bit lazy and say, do we really need to redo all of the calculations? Because those diagrams that I showed you earlier, these kind of things, it looks bad enough that it looks like you've got a whole bunch of things to calculate here. You know, when we calculate these reaction pathways, we've got to do lots and lots and lots of calculations even then. We've got a whole lot of different potentials that we want to consider. We've got a water layer, which makes our calculations really problematic. So we really don't want to have to start this all over again from at the start because it just wouldn't be feasible to do this. So what Ray and I did over the summer was we wondered whether we could actually do most of the work with any old approximation that we wanted. So for instance, the one that they used there. And then could we simply take those structures that they found and recalculate the energies on top of that without having to do the whole wiggling around optimizing this whole system. And I'm well over time, so I will skip to the punchline of that, is that we found that thankfully we could. We basically compared for a few key reaction steps, so some of the really important things in this pathway, we explicitly optimized with that new method, compared it to what we would get if we just took the old method and did a wee tweak on the energies, and it turns out that our energetics were really, really, really similar. So as I was saying to Michael before, this was really good sort of a seed project, because if we couldn't have done this, if we found out at this stage that we couldn't, then that was probably going to be it for the project, because we just couldn't afford to redo this whole thing with this new function, with this new approximation. So I'm going to stop here and basically say what we've started to do now is we've started to recalculate all of these things and basically see how our picture changes when we change our approximation a little bit. The short answer is yes, it does change. And a few of these paths look closer than before, and what it looks like is that we won't actually just get the dominant methane production, but at least at this potential we'll get a fair bit of ethylene and a bit of methanol as well, and some CO, but if it's around about here on the diagram, but that's actually what you observe experimentally as well. It's not like it's only methane formed, but there is ethylene formed, there is CO evolved as well. So this is still ongoing with me trying to tidy all of this up. So I won't go into any more of this. Sorry, Jeff, it's your project. But I will finish just probably by telling you there's some other very clever and wonderful people in our group that are working on various things and that are here today, which is great. But hopefully I have showed you that with this computational approach we can design some new catalysts, we can really understand what's going on the surface of these catalysts and what the various sites do, and we can understand these really complex reaction mechanisms. So maybe we think now we know how to find some of these green catalysts. We're going to solve all the problems of the world now, apparently. So thanks to everyone who worked on it and the funding, especially you guys for that wee bit of money. It was really great to work on this. So thanks for your attention.